Swayam Prabha. Digital India. Educated India.
Hopefully by now you are convinced that in rigid body rotation it is the angular momentum that is the key quantity of interest and that determines the dynamics. Let us now see some other quantities or equivalent quantities in rigid body dynamics which are equivalent to one particle dynamics that will be useful. So, let us look at kinetic energy, and again I am going to consider this simple case of particle moving about one axis. Kinetic energy is equal to 1/2 summation I mi Vi square, and therefore I can write this as 1/2 summation mi Ri square, where Ri is the perpendicular distance from the axis times omega square, which is nothing but, if I put the bracket here, 1/2 I omega square, which is equivalent to 1/2 mv square of one particle dynamics. What about work energy theorem? Or work done itself? Again we will use the basic definition that work done is nothing but summation f on ith particle, distance moved by it in the direction of the force, dri summed over. So, if a body is rotating like this and I apply a force on this, the only component, since it can move only in phi direction, only component of force that will work is that in the phi direction. So, I can write in this case is summation f I phi direction, where by phi I mean the, in the sense of cylindrical coordinates, this is phi x y and this is the z axis about which this is rotating. F I phi, distance is going to be r I d theta, which is nothing but, this quantity is nothing but the torque. So, torque times d theta, this is going to be partial work done. For full work I put the integration. Once we have determined the work energy theorem is that change in the kinetic energy, that is delta of 1/2 I omega square is going to be equal to work done, which is nothing but tau d theta. Similarly, if I apply an impulse to a single body, what happens to its momentum? Its momentum changes by the amount of impulse f dt. In the similar manner, if I apply an impulse and that provides a torque, its angular momentum is going to change by the torque impulse. So, let us see in the case of rotation about a fixed axis, what are the equivalent quantities of single particle So, let us see what are the equivalent quantities in single particle and rigid body dynamics. So, let me write single particle here and a rigid body. Here I have momentum P, here I have angular momentum. L. Momentum P equals mv, and the case that we have discussed so far, L along a particular axis equals I omega. Momentum satisfies the equation dp dt equals the force angular momentum satisfies the equation dl dt equals the torque. If there is an impulse, in that case the change in momentum is equal to the impulse, and in the case of rigid body, if there is an impulse, change in angular momentum is equal to torque impulse. The work done in this case is f dot dx integral. In this case we considered again the case of single axis is tau d theta integral. Kinetic energy is 1/2 mv square. Kinetic energy in this case we derived was 1/2 I omega square. Work energy theorem tells you that delta K E is equal to work done. Same thing here, delta K E is equal to work done.